All right, I think folks are shifted over here, so and I'm assuming I should just go ahead and start. I don't think there's anybody who's going to introduce this session other than me, so I ought to get going. So my name is Michael Hubenthal. I'm the Senior Education Specialist at the IRIS Consortium. And I think most folks probably, and that I see a lot of familiar names on the screen, so I think many people know IRIS, but just in case you don't, IRIS is the Incorporated Research Institutions for Seismology. We manage the SAGE facility, which is a NSF-funded research facility to support seismological research, both within the US and around the world. And this is, pools of instrumentation, access to seismic data, and education and public outreach. And so my role is working with the public education and outreach program. I've been in IRIS now for about 18 years. My background is in science education, though I've worked at IRIS for quite a while now, so I've picked up quite a bit of seismology. I'll do my best to answer some of the more technical questions come up, but at some point we may bump up against the limits of my understanding, depending on the questions that we get. And so I can be happy to follow up with people, take a few notes, and follow up with folks afterwards if we get beyond that. So this session today is one that I've been kind of thinking about for quite a while. It's, this question of how do we get beyond S-P earthquake locations in the classroom, especially when there's so much exciting work being done in the field of seismology, things that maybe we want to be considering for our earth science classrooms that would be better, maybe better or alternative, or in addition to, I suppose, as well, to doing some of the more traditional labs that we've already been working on. So by the end of this session, I'm hoping that you might be able to summarize why earthquake locations are important in seismology. I'm hopeful that you'll be able to describe a few shortcomings of the S-P lab, and I think that it would be great if you could compare and contrast the S-P lab to maybe a lab using some more modern approaches to earthquake location. And then finally, I'd hope that you could leave with at least one or two ways that you might look to modernize your own seismology instruction in the classroom. So let's begin with this first idea. Earthquake locations are really fundamental to most seismological research. We can't have studies of earth structure or seismic hazards or making tectonic interpretations without knowing where earthquakes are located. And this is sort of a given today because most seismologists, or many of them, rely on sort of networks to do locations for them. And so this is sort of something that just kind of happens in the background. We all get a USGS alert and it tells us where the earthquake was located and what the depth of it was and when the origin time was. But that has to actually get calculated. And it's important to make sure that all of these other pieces can flow from it. So I just chose a quick figure here at random. This study wasn't one that was really all that important, but really just to show you, in this case, the earthquakes are represented by stars, and the lines are being traced up, and you can see US array over here on the right. These are where there's a set of seismic stations that are recording these events. And so these red and black lines represent ray tracing going from each individual earthquake up to the station. And so in order to be able to accurately come up with paths that those earthquake waves have traveled, we have to know exactly where the earthquake took place. And so that's really important for all of these aspects of it. In fact, it's so important that when seismologists think about teaching earthquake locations, they really find it to be so fundamental that they want students to participate in these sorts of exercises. They want them to know how earthquake epicenters are located. So seismologists think this is a really important topic. And that's probably one of the main reasons why it appears in our earth science curriculum so prevalently. But before we get too much further, I want to say something about the type of earthquake locating that we're actually talking about here. So this is S-P locations. And so I think most people in this room are probably going to be familiar with it, but just in case you're not, It might commonly look something like this. We have 3 different seismograms here, and we mark when the P wave arrives on it and when the S wave arrives on it. And we take the arrival time for the P and the S over here, and we measure a distance that is away from an epicenter. And then students go to a paper map, and they're going to set a compass, and they're going to draw circles on that map. And the points where those 3 circles cross is actually where the epicenter is located. So this is really what we're talking about when we say the S minus P location method. You'll also hear it called the triangulation method as well. And this is, the traditional sort of seismology that most of us probably think about. However, my goal by the end of this session is to maybe get you to rethink incorporating this lab in your classroom. I'd like to show you some alternatives that you should be considering in addition to this or instead of potentially. And the main reason for this is that there's a couple of things that I would say are problems or challenges, maybe even shortcomings to this lab. And these are everything from technical to practical to sort of pedagogical and curricular sort of shortcomings. And these come up primarily because this same lab is used, if you look across textbooks, it's used in the middle school, it's used in the high school, it's also used at the introductory geoscience level at undergraduate. The exact same lab, almost identical, can be found in all of these textbooks, including the exact same maps, and it's not uncommon to be even locating the same earthquake sometimes across multiple textbooks. So let's go in and talk a little bit about some of the shortcomings that I can see for this activity. So first, this method is commonly introduced as the way earthquakes are located, and it commonly doesn't come with a caveat that this is not how earthquakes are actually located today. So this method was developed around the turn of the century. So P and S waves were first used by Omori and Laska in 1903, and sort of simultaneously, Milne, a British scientist, also published a paper using P waves and surface waves. And you'll notice that he basically is using the exact same process of looking at a set of travel time curves. It was easier to pick surface waves. S waves are pretty problematic on vertical instruments to detect the S waves. And so for some of these older instruments, they were really problematic. So thus they were using surface waves. I'd also note at this time in 1903, they also weren't called P and S and surface waves. They didn't have that nomenclature in 1903. And so these were going to be called preliminary waves for the most part that they were using. And so over here on the right-hand side, this is Omori's figure where he's actually located the earthquake in southern Japan down here using a triangulation method. And you'll notice that his triangulation method, of course, doesn't all cross in a single point. He gets a little triangle down here, which isn't uncommon. I think a lot of our students in the classroom using S minus P feel badly when their circles don't cross, and that can be from a wide variety of errors that are introduced in the lab. But at this point in 1903, this was a pretty good location for this event that was pretty far away from the various stations that were used. So the main shortcoming is not only is it an old method, but this method didn't last very long. So in 1910, there was a German paper by Ludwig Geiger, which produced the first sort of more modern earthquake location system. And so this is where they're finding an epicenter from first arrivals, starting from a initial solution and then minimizing the residuals. They're using a least squares fit way. This German paper was then translated into English and published in English in 1912. And so sort of from this point forward, seismic networks really began to use Geiger's method and never really looked back to S minus P. In fact, when we asked, in sort of working on this talk and some of these ideas, I asked some of the older USGS network location guys about this. And the only reason that they could think of where they might use an S minus P location would be if for some reason they didn't have absolute timing on all the seismographs. So time turns out to be a really important piece. And so that's why in 1903, we used S minus P, because we didn't have absolute timing. And by absolute timing, I mean the exact time at all the stations being recorded in the same way. And so we only had timing individual at each station. But once we got out to about 1910, 1912, we really had much better timing on seismic instrumentations. And so we could do a better job of locating earthquakes by using this Geiger's approach. So the main short takeaway here is the S minus P location is just really out of date, and it isn't the way that earthquakes are currently located. So the next thing that's a technical shortcoming with this approach is that students really are working with either heavily simplified or manipulated data. It's not uncommon to see in labs, to see diagrams similar to this one that I've chosen here, where we're taking a look at, in this case, these are hand-drawn wiggles. They're not really even looking at real seismic data. Or if it is seismic data, it's been enhanced to really exaggerate these different phase arrivals. And what we end up teaching students commonly is that the first bump is P, and then the second bump is S, and then the third bump are surface waves. However, what we lose then is what it really looks like when we go to pick earthquakes. And you can see over here on the right, this is from a recent 7.8 that happened in Alaska. And you can see these waveforms, and real seismic data is significantly more complex. And we're looking at it not only as one trace, but we're actually looking at three components of motion. So this is BH1, stands for broadband sensor, horizontal channel 1. So this is either north-south or east-west. And broadband horizontal channel 2. This is going to be the opposite. So one of these is north and south, and one of these is east and west. And then Z, this is our vertical channel. And so what you might notice here, if you look closely at these, is that the way that the P wave is recorded varies by which channel you look at. And so because the seismic waves arrive, if my hand is the station, and the seismic waves are coming up from below, most of the energy from a P wave is going to be compressive in the vertical channel. And we see really strong compressions here in the vertical channel, and you'll notice they're smaller in the two horizontal channels. And the same then goes to play for when we go to pick S waves, except for it's in the opposite direction. So S waves are better recorded on our horizontal channels. But even then, knowing that, they're still difficult to find. And so one of the shortcomings with the S minus P approach is that you're dependent on being able to pick both Ps and S waves cleanly on seismic data, which turns out to be challenging. And as a result of it being challenging, lots of textbook authors or textbook companies go to sort of these overly simplified hand-drawn signals of a single trace when really we're recording three components of motion. So another shortcoming of the S minus P lab. A third shortcoming, technical shortcoming of the S minus P lab is that circles are often drawn on flat maps, which lead to issues of distortion, right? So basically, when you look at some of the literature, some of the seismologists recommend if we are going to do S minus P activities, we really need to be locating earthquakes within 200 kilometers in order to actually have our circle work reasonably well to actually triangulate a single point. And just to emphasize this, on the right-hand side here, I'm showing a global map. And this is a tool that IRIS offers if you'd like to do earthquake locations online. One of the ways to get around this distortion is to use a computer. But what you end up noticing is that at these sort of scales, we're not really drawing circles. We're drawing shapes that are distances that end up looking more like ellipses commonly, depending on how big they are, because of the shape of the Earth. And so we're actually not dealing with a flat map, so a circle doesn't really work. And this comes up to why we have this idea that our epicenter should cross at a point, but in reality, most students really aren't able to achieve that degree of accuracy in their S minus P location lab. So a couple other shortcomings that I'd want to point out. One, the labs tend to be fairly cookbook. Really students are marching along, they're following procedures, and they're drawing their circles, but the opportunity for variation isn't very great because of the methodology that's used. And this could be extended at the end of the lab, I think, in some pretty simple ways, but most iterations of this exercise sort of end with drawing the circles. Another shortcoming is that the travel time curves often are presented as black boxes. They're this magic graph that works to locate earthquakes. And so students use it, but without getting very far into where the travel time curves actually come from. And so that's something that could be addressed by using things like this animation here that Iris has produced that goes through how we use hundreds of earthquake arrivals that we track, and we overlay those to produce our travel time curves that then work with the S-P. That would be a way around that, but as currently used, there isn't much discussion of these travel time curves in most of the labs that are out there. An important one as we look ahead into what our science instruction is going to look like going forward. Earthquake locations really aren't part of the NGSS. There's no real mention of them in there. The performance standards don't directly address it, though they do obviously make use of where earthquakes occur as part of many of the performance expectations. But the actual process of locating earthquakes isn't part of the next generation science standards. And so as we move ahead towards creating more NGSS aligned classrooms, we might want to rethink things that aren't included in the NGSS, especially if we're not doing a great job of addressing some of the standards that are included in the NGSS already. So maybe swapping something out, one thing for another. And finally, a big shortcoming in terms of just in terms of teaching seismology is, this same seismology lab gets taught at the middle school level, the high school level, and the undergraduate college level. And of course, if we think about alignment of curriculum, this is problematic in that we never really build on any of the seismology that we've already taught. And so it doesn't create space for us to teach some basic seismology and then maybe go a little deeper into something, or maybe introduce other other topics that we might want to include. If we, the seismology lab that gets done in each of these classrooms is earthquake location, what ends up happening is that students think seismology is locating earthquakes. And what we know is that seismology is contributing to all sorts of fields well beyond just earth structure, right? Seismic techniques are being employed to study climate change through measuring storms in the oceans, by examining ice quakes that are happening in glaciers, glacier calving. We're able to help study hydrology by measuring water flow in fluvial systems, sediment transport, for example. These are all places that seismology is playing a role in the geosciences broadly, but there's never really space to touch on those because we're spending a lot of time on earthquake location. Oop. All right, so those are some shortcomings. So this also should beg the question, why do so many instructors use the lab? If there's problems with the lab, why do we use it? Well, I've spent a bunch of time over this past summer digging into sort of the origins of this lab, or trying to find them as best I could. And you can't really, or I wasn't able to really find anywhere that was, I could confirm was the first iteration of it. But in doing some digging, it's been around for a long time. We've had it included in geoscience education for quite a while. So I think inertia is probably one of the main reasons that we continue to use this lab. We've seen it in college textbooks as early as 1920 in a textbook of geology. And we also know at high school level, textbook some of you may be familiar with, the Nemowitz and Stone text, Earth Science, the World We Live In, had a description of the S-P earthquake location process in it. The hands-on version of the S-P lab as the actual activity probably has its origins in the Geology and Earth Sciences source book which was the precursor to the textbook that many of you are familiar with, Investigating Earth, which is the Earth Science Curriculum Project text. And that's from the early 60s. And so this is where we begin to see the first hands-on labs for students to actually do. And I'd note that, one of when you look at the lists of the geoscience participants on these two publications, there were geophysicists that were involved in this. And so, we saw early on that location is really important for seismologists. And so it wouldn't be surprising if they would have encouraged students to have something to do with location in their textbooks. Additionally, at the time, there probably wasn't too much else that you could do given the technology that was available at the time to include earthquake locations. And then finally, we have high stakes tests like the New York State Regents, which can drive a lot of curriculum. And so we see an initial text question about earthquake locations appearing in 1967. We have a triangulation map question showing up in 1968, shortly after the Earth Science Curriculum Project came to be published. And then finally, we've had hands-on labs. So annually since 2001, there's been a performance expectation in New York State for students to actually locate earthquakes. So here on the right-hand side, I'm showing earthquake locations from a variety of different sources. A is this original 1903 Amori map. B is a 1930s college textbook. I chose this one because the examples and the stations used are really similar to the 1967 New York State Regents map that was used, which again is also really similar to this is a modern textbook. This is from 2010 as well. And so a much more modern high school earth science textbook, again, using a really similar sort of set of maps. You can see they're following along one after the other and choosing stations and choosing locations as well. So another reason that we might think about including S-P earthquake location is that it's pretty efficient from a teaching standpoint, right? It's easily understandable. Students have a pretty, sort of have these natural experiences which would allow them to envision, two waves leaving a source and one wave being slower than the other. So we might have they left at the same time and our S wave was the walker moving at, 2.5 miles an hour. And the P wave was our runner at 6 miles an hour. They could get across this idea that the P wave would get further in front of the S wave, the longer they are traveling for. And so this is something that's, students can kind of grasp onto and get a sense of pretty easily. And so that's certainly one reason that I'm sure it's used. Another reason is that it really does underpin a lot of important concepts, including those that are included in the NGSS. So, it's underpinned by things like this idea that earthquakes generate seismic waves, that seismic waves propagate outward through the earth and cause ground motion even at great distances, that there's different types of seismic waves that are produced, and that each seismic wave type has a different mechanism of propagation and speed. And so this is certainly, some ideas that could get touched on in a lab. They often, they may or may not be depending on the implementation, but it isn't uncommon to have these concepts being sort of tied to it. And then finally, and this one I think is an important one, it's a chance to use empirical data in a section of the earth science curriculum when you may not have many other opportunities, right? Students don't have a chance to go and collect a lot of their own data in this area. And so adding seismograms in creates a lab opportunity in a section of the curriculum that might otherwise not have labs in it. So I think that's a reason that this is stuck around for so long. And finally, an important one that in some of my conversations with some peers about why we've been using this lab for so long is that it has a lot of skills in it, right? When you do this S-P location lab, students get to develop skills like they have to make really careful measurements of when the P waves occur. They have to make interpretations of a graph, so they have to be able to read the travel time graph. They have to make conversions between the time on the graph and the time scale that's on the travel time curves. They have to do some map reading of lines of latitude and longitude. Again, they're going to have to make conversions from the travel time curves to the map. They need to set a drawing compass and maybe even learn to use a drawing compass. Some of them may never have used one. And there's also some chances to talk about things like accuracy and precision and error in this lab. So there's a lot of skills that get touched upon that are included in this lab. And I'm sure that's a reason that this lab has again hung around for so long. So at this point, I wanted to pause for a minute and see if people had questions or give people a chance to sort of process some of that, some of those ideas.
Michael, I think it's good. You're trying to motivate us to make change. So far, so good. Thank you.
We use this at the college level, so it's exactly the same way you just described it. Very simple. Even then, some people have a hard time following it for students.
Mm-hmm. Okay, let's thank you for both of your comments, and I appreciate that. And again, if you have questions, I'm happy to take them as we go. But I'll do these pauses periodically to allow time for people to ask questions. So you can also feel free to write them down, and we'll jump into them. And comments are welcome as well. All right, so if you do want to modernize your education, what else might you do? And so this is what I see as option one, and I would say this is probably the best option in your NGSS aligned classroom. You might want to target this high school standard, which says this is a performance expectation from the high school Earth Science Standards. It says develop a model based on evidence of Earth's interior to describe the cycling of matter by thermal convection. And they specifically call out using examples of evidence that include maps of three-dimensional structures from seismic waves. And so this gives us a strong place to tie into using seismology in an NGSS aligned curriculum. And you can get a lot of the same things that we talked about as being reasons why the S-P lab has hung on for so long. You can get all of those same things in a lab that targets this exact NGSS standard. And so we have a lab called Discovering and Measuring Earth's Layered Interior. And it really gets at this question, how do you know what's inside of Earth, right? What evidence do students have for what's taking place inside of the Earth and what's happening there? And really what this is it's a chance for students to basically reproduce Richard Oldham's experiment or study from 1906, where he finds the first direct evidence for the Earth having a layered structure. So basically you're finding the core of the Earth inside of Earth's layered interior. Now, prior to 1906, we did have, it had been proposed that we had a core inside of the Earth based off of other geophysical aspects or other data sets, but we hadn't had any direct evidence. And that's what Oldham contributed in his study from the Aswan earthquake. And so here's why you might use this activity. First, it does use seismograms in the format of a record section. So a record section, this is this plot of seismograms down here, where we have distance away from the earthquake and the recording of lots of stations moving out away from that earthquake. And so we're going to use a record section to find the core of the Earth. But in this activity, we're only going to use P waves. And so P waves are really easy to pick because it's a change from background noise to some sort of recorded vibration of the ground. And so they're much easier for students to identify. And so we can get away from having hand-drawn data. Again, it's a classic study. So while it is dated, it is a classic study. So I would put it, you could place it into that context, similar to like if you were going to teach in chemistry and you were Rutherford's gold foil experiment for looking at the interior of an atom or something like that. So reproducing historical work. It employs a lot of the same skills. So students do have to read graphs. They have to make careful measurements. They use rulers in this activity. They actually use scale models in this activity. One of the things that I really like about this lab is you ultimately, I don't know if it's on the next slide. Oh yeah. So in the next slide, we divide them up into two groups, where one group is a seismologist group and they actually look at the seismic data. And then there's another group where they build a scale model. They're the theoreticians.
Two of these, we put the two of these together, and the students then compare the observed data to model data, and then.
And so that is, that's one of the reasons that we really like this particular lab. And I think the final piece that's really important is in terms of the broadest learning that students are going to come up with, we have, the results are going to be arguably more important here, looking at Earth structure, than what we're going to find in doing a simple earthquake location. And then just a couple of pieces that you might use to sort of supplement students' learning. We have a number of animations that you could use to sort of add on to this. And then we also have an interactive tool to explore seismic waves passing through Earth's interior so that you could extend learning. You could talk about some of the more complex layers and build on that simple reproducing of an older experiment to get into the ideas about how we know that not only is there a core, but there's an inner core and an outer core, and we can begin to build out into shadow zones and things like that. So it's a good stepping stone. And I'll pause for a minute here as well.
I'll just say that it's a lot nicer than lecturing. You're going to make them figure it out on their own. So I appreciate that.
Okay. So let's talk about now, if you do want to, the second option I would say is if you do want to teach earthquake locations, then I think we should consider updating the way we teach earthquake locations. There are some better ways to go about doing this. We can have it sort of underpin a couple of the NGSS standards. So performance expectations in the middle school level could be underpinned by this. So sort of as an extension. Largely in the middle school, they're using earthquake locations to get at plate tectonics. And so we could say, well, how do we know where those earthquakes occur? We could extend out in doing a location lab. We could also tie it into sort of some of the science, technology, and society connections within the NGSS about how seismometers work, and maybe the changes in timing and whatnot connected to a seismometer could also be used. But in this case, we really want to sort of dig into this idea of earthquake location. Can somebody give me a thumbs up if they can hear me? I'm getting a weird warning from Zoom. Okay, good. All right. I was getting a weird warning from Zoom that audio was having trouble. All right, so the first thing that we might do is we might use a different way of locating earthquakes. So this is a simple alternative to S-P locations, and it's going to be called the bisector method. And we're building a new tool that we're actually beta testing right now with users. Students are providing us with feedback on it, and we should be releasing it fairly shortly to use in the classroom. So it's going to locate earthquakes. Again, not the way that earthquakes are located today, but it's a much simpler process, and it lays the foundation for the way that we do actually locate earthquakes. So here's how it works. We have an area. And we know each of these triangles is a seismic station. And we know that an earthquake has occurred somewhere in this space because each of these stations has recorded a seismogram of it. So in this case, these are all vertical channels, and each one of these recordings is one of these stations. So we know an earthquake has happened, we just don't know where. So how are we going to go about finding it? Well, in this case, we're going to use a really simple process to do that. We're going to compare the seismic arrivals at station A versus station B. And we're going to simply answer the question, which one did the energy arrive at first? What this is going to allow us to do is to narrow down a space on the Earth's surface that where the earthquake can't have been recorded. So imagine this, we have two stations, triangle 1 and triangle 2. And I'm going to compare the seismograms from each of these. And I look at them and I say, okay, whoops, let me go back one. I look at these and I say, okay, this purple station here, the P wave arrived here first. So I'm going to use a geometric approach called a bisector. So I'm going to take a straight line path between station A and station B. And midpoint, I'm going to draw a 90-degree line that is going to intersect the path. And I'm going to say, okay, if it arrived at station A first, that means that the earthquake can't have happened in this shaded out area. And so if I have a number of stations, I can begin to narrow down the region of the Earth in which the earthquake can't have been, and it's going to leave me an area where the earthquake had to have occurred. And what's nice is P waves are really easy for students to pick. You know, we can see where we have a change from background noise on these seismograms to, in fact, these picks aren't even great as I look at them closely. I did them late last night. This one is a little too late. It should actually be up in here. But it's pretty easy to see the change for students, and it's a pretty simple process for them to think about. So if you bear with me a second, I'm going to switch screens, and I'm going to show you a live demo of this. Okay, so here's the screen that we looked at where we're going to pick our first arrivals at. And just to give you a sense of how students will pick, they're going to zoom in, and they're going to go in and they can slide the slider and say, where's the change from background noise? That looks pretty close. I can zoom in here as well. And I can see I need to adjust this one just a little bit. That looks pretty good there. And so I could go through, and I've already picked most of these pretty closely before the call, just so I'm pretty well set up. But you can see that I've gone through the list. And the other thing they'll do is they'll look for bad data. So we're dealing with real data. Sometimes the station is wonky and the trace is out of whack. It's completely flat, it's missing. And so you can delete it if the station is noisy and get rid of it. So the next thing that we're going to do now is we're going to go to the map view and we're going to make our bisectors. And so in the map view, I'm going to simply take pairs of stations, just like I showed before, and I'm going to begin to eliminate parts of the map where the earthquake can't have occurred. So my question is, which one of these stations did it arrive at first? Well, we look at the time since the earthquake, and we can see that it obviously arrived at station WCI first. So I'm going to shade out half of the map where the earthquake can't have occurred. And then I'm simply going to choose another set of stations. And this one's a little closer. This is pretty equidistant. So I'm going to have to do the best I can. And I might have to really zoom in to get a good idea of what's happening. And boy, that is really close. 831, 831. And then I got to check carefully. And I'm going to say, oh boy, I'm going to go. I'm going to say it arrived at NHSC first, but that's a dicey one there. But we'll eliminate part of the circle, and then we'll continue to do this process. Let's do one more pair here quickly. We can see that TKL is where it arrived first, and let's try to get it down to a small area here so we can see. And NHSC again first, and let's maybe get another pair, NHSC, and we can maybe get, oops, DKL. And so basically we're going to work down until we end up with a very, very small area remaining. And you keep going through the various pairs of stations to get it down to an area. And so once I have an area that I think it's going to be located in, I can choose select a solution. And I click on the corners of that area to identify the region I think it's in. And then I'm going to compare it. And I must have picked that one that I was going back and forth on a little wrong. If I zoom in, we can see that the actual location is really right on the very outside edge of the area I got. But it gives me the size of that location. And then it's going to allow me to go down and say, look at other possible combinations that I didn't include in my solution. And here's the one that I got wrong. So I actually had one pairing wrong that I could go back and look at. So does this give us an exact point on the Earth's surface where we located the earthquake to be? No. It gets us to a small area that we could say is a reasonable solution. And it's going to depend on station coverage. So we might ask students at the end of this, how could I have reduced the area even smaller? Well, I used 7 stations. What if I had 20 stations? Could I have come up with more pairs to narrow the area even further? And the answer is yes. So if we're going to change, we might consider changing what we do, because one thing that the students commonly take away from this activity is, especially if you're doing this over a very big region, so using stations from a much bigger area, we might say, well, notice where this earthquake was. It was actually really close to the closest station here, right? So why we could have almost been as accurate if we had just started by assuming that the closest station was where the earthquake was at. And that idea comes up, and that's a good starting point to answer the next piece, which is, well, how do we actually locate earthquakes? And so that's the next place I want us to go, is to take a look at how do we actually locate earthquakes. So the way we do this is we're going to use P-wave arrival times, just like the bisector method. We're not going to even look at any other phases, but we're going to add in a velocity model, and we're going to solve for 2 things. And so the difference in this case is modern earthquake location solves for the origin time and the event hypocenter. So we need to know when the earthquake took place, because that's not known. The station can tell you what time they recorded the waves, but they don't know when the earthquake happened, and they don't know where it happened. So we're going to use computers and seismic data and a bunch of stations, and we're going to find the answer to those 2 questions. So here's how it works. Again, same idea. We're going to analyze the seismograms, and we're going to make observed pick times. And so my pick time is going to be in hours, minutes, and seconds. So I know what time, because I have absolute time across all my stations, and I know when that took place. Now, what I want to get is a predicted pick time for when the seismic waves should have arrived at each station. So to get here, this is where my velocity model comes in. So I'm going to start with an assumption. And my assumption is going to be that this closest station was where the earthquake was. So if I measure from my closest station to the station that I want to get a predicted pick time for, I get a distance. If I take my distance and I go to a velocity model, I can then determine when the seismic waves, had they traveled that distance, what time would they have arrived at that station? And I get travel time in minutes. Now, this is a plot of 30,000 earthquakes. Each dot is 30,000 earthquakes stacked one on top of the others. You'll notice that it looks like a travel time plot. This is how we come up with the travel times curve, by measuring lots and lots of earthquakes. This was one of the original ones that was used, but we have an updated version with something like 300,000 earthquakes plotted on it that really lay out these seismic phase arrivals, these lines that you see in it. This is a super simple velocity model that I'm showing you here. It doesn't account for horizontal heterogeneity in the Earth. That is, as you go right or left, that the velocity might change in small amounts because the waves are traveling through faster or slower material in the Earth. So the models that are used for earthquake locations are much more complex than this, and they do account for more 3-dimensional velocities than we're taking here. So I'm simplifying this quite a bit. All right, so now this time I have a travel time in minutes, but I need to get a pick time, which has to be hours, minutes, and seconds. So I have to go from travel time in minutes to some clock time. And the way we're going to do that is we're going to take my observed pick time that I picked off the seismogram, and for each station, I'm going to subtract the predicted arrival time to get a station origin, model origin time, or when I think the earthquake would have occurred for that particular station. And then I'm going to take all of those for all the stations, and I'm going to add them up, and I'm going to divide them by the number of stations. And I'm simplifying this a fair amount, but I'm going to basically average them to get the estimated model origin time, or what time I think the earthquake took place if we assume the earthquake happened at the closest station. So I'm going to use this assumption. I'm going to build it all off of that basic assumption. Now, the final piece is that I'm going to compare the observed pick time to the predicted pick time, and I'm going to get a residual. So you can think about it like this: pick time observed minus pick time predicted, I'm get some residual. And again, this is, I'm oversimplifying this, but it gets the idea across, I think, that if I have a small residual, it means that my seismic picks were good and my initial location was good. So that station must be pretty close to the epicenter. If my residual is large, I either didn't pick very well and or my initial location was bad. I was way off from the actual location of the earthquake. So then the next job is to use a computer to then reduce the residuals until some threshold is reached. So we could do that in a couple ways. We could look at our picks and adjust anything that seems out of line, or we could adjust the starting location in a direction that's likely to further reduce the residuals. And then we're going to repeat the calculations and begin a loop. So calculate residuals, compare the residuals to the threshold. If we don't meet our threshold, we go back and we change the location. So we move it not from the closest station, but to some other point. And then we recalculate our residuals. And then we come back to the residual threshold and we loop until we're happy. And once we reached some acceptable residual, we get a solution. And again, it isn't the location of the earthquake. It's the closest place that we think the earthquake took place within the error that we are comfortable with, the network operators are comfortable with. So can we really know the exact point? Probably not. Can we get really close to it? We can. So here's what this tool might look like in a tool. But I'm going to pause right there and I'm going to open it up for a few questions because this may be new for some people. And so I want to see if there are questions that people have before I demo it.
I just assume that you're going to coach us pretty well on what's a low residual and what the threshold.
I'm not hearing you, Steve. Hold on.
Can you hear me now? Give me a head nod. All right.
Okay, how about again? How about now?
Can you hear me? I'll put it in chat box.
I can hear him.
Okay, I got it now. I was having an audio problem. Okay.
I'm just wondering, is there good coaching on what is a low residual and what the threshold would be?
Mm-hmm. Yeah, and so this is one of the areas with our tool where we need to play around to help students decide when to stop. To be honest, what the beta version I'm going to show you of the tool to have students do this is a little less further along because it's a little more complicated. And so this is an area where I think people who are willing to test it for us could help give us some feedback on how much cueing do you need to know when you've gotten to a place where you want to stop. And I think you'll see in the demo what that kind of looks like.
So I'm a little confused. It seems to me like you were talking about a slide that isn't the one I'm looking at.
Okay.
I'm not seeing residuals or any tool to get them.
Okay. Yeah, I haven't demoed it yet, but I can switch and go to a demo. All right. Oops. Okay, and okay. So here is a demo. I've already picked a bunch of, picked an earthquake, and I've got a bunch of stations. And I did something intentional here that I want you to see before we go into it. So notice down here at the bottom, I picked all of these stations up here at the top. I picked the P waves already, really pretty accurately already. But down here at the bottom, I have 3 that I didn't pick. So notice the P arrival is way, way too early, way out in front. And that's important. That's going to be important. In fact, I'm going to just do one more to get it close. So we have 2 of them that are going to be really wrong. The pick is really problematic. So I'm going to now go to the next screen. And so now imagine right now what the computer's doing is it's calculating the residuals. It's saying, I'm going to assume the earthquake is this initial location, which is the station highlighted with a yellow triangle. And then it says, okay, I have residuals, and the residuals are represented by these arrows. And my place marker is the location that I'm going to try. Now, this is where I think the computer works a little too slick. Our programmer built it a little too slick. It's not, every time I move the mark, it actually calculates new residuals in real time. Now, for students, I think that might be a little too fast to have them understand what's occurring. And so you can see my residual is up here in the upper right-hand corner, and the number changes as I move the mark, and I can make it get smaller and smaller as I move in these directions. Notice the arrows get shorter and shorter and shorter, except for this one. And this one is really long for some reason, and I can't move it to get it smaller. So if I click on that arrowhead, you can see that the pick is a little off on that station. So I might try to adjust the pick on that just a little bit to help correct that. That's one of the ones that I had made the bad pick on intentionally. And so I can move the marker around until I am happy, you know, kind of with where I'm at. And then this green little circle here that I'll move so you can see, this little green circle shows the best residual that I've had so far. So I don't have to remember where that was. I can actually do it this way. And then if I want to go back and check any of my picks, I can pull up each station and say, okay, how are we doing with these particular picks? Am I okay? Do I like them? Is something wrong with them? Nope, that one's good. I like that one. I'll take a look at another and maybe adjust this a little bit. Fix that one. And so then really I'm changing the initial location for the model. And when I do, I get all these new errors. And then the final thing I can do is I can change the assumed depth of the event. So I can say, okay, it's going to be a really deep event, which we know anything about the tectonics of North Carolina. We know that it's never going to be 384 kilometers deep, but I could leave it there and you can see what it did to my residuals, right? My residuals went way up because I went with a bad depth. And then when I'm done, I can compare it to the accepted USGS result. And so, you know, I was in the ballpark, but it tells me I was off by only about 17 kilometers, but I was way, way too deep. And so if I look at, you know, a series of targets, I can see, yep, I'm actually pretty close to where that event was. I could have been over here. And if I had taken my residuals all the way down, or my depth all the way down, I actually would have close to a 1, a little below a 1 for my residual. And that's going to give us the actual location of the closest location of the earthquake. So this gets that idea that the sequence of the 2 earthquake location methods, the bisector method gets you to think about P waves only, and the role of that you can determine which station is closest to the event without actually doing anything else, which then builds to this idea of how we actually locate earthquakes today using the residual method here that was really developed in 1912 by Geiger. So this builds on that. It's a little more complex now. but it's the same basic idea that we used in a little while ago. So with that, I can.
Maybe on the, you said your programmer made it too well. Maybe if he could have slowed down the processing of it so you could actually see the arrows drawing or moving. So it's not like just instantly. So they could see the process actually work.
Is he still here or did he get
I
booted?
think he just cut out.